So what am I talking about? Forgetting about the quotient and only remembering the remainder. I'm talking about modular arithmetic. So what does this mean? It's going to take us a second to get there. We're going to make some definitions first. So we say integers a and b are congruent mod m. Here m is another integer, maybe not 0. If, so I'm going to write a couple of conditions. They're all equivalent. So you can define it in any of the following ways. So a and b are congruent mod m if m divides their difference. And this is the same as saying that b equals a plus some multiple of m. And this again is the same as saying, so this equivalence is fairly clear. This is the difference between a and b. We're just saying it's divisible by n. But this next equivalence maybe is like takes slightly more thought. A and b give the same remainder. When divided by n. As in division theorem. So let me zoom out for a second. Maybe just scroll back up. So the division theorem says that for any two integers a and b, we can find an expression like this, where a is some multiple of b plus some remainder. And there is a unique expression where the remainder is constrained to be in this range. So under the division theorem, a and b can both be written as something times m plus the remainder. And this thing might be different, but if the remainder is the same, then we say they're congruent mod m. So it might be a good exercise to check that this condition is equivalent to the other two, if it's not clear to you already. But let's illustrate this with some examples. Oh, and I should say, we write a triple equal sign b mod m. And a quick note about, so congruent is just a word that means things are somehow the same. So they agree with each other. This part, I don't have as good of an explanation for. Mod is short for modulo. So something to do with a modulus. But I don't exactly know why it's the word we use. Gonna just have to get used to it. But this is the notation. A is congruent to b mod m. So, for example, 3 is congruent to 7 mod 4. So let's check this. Their difference is 4. So 4 clearly divides that. That checks out. Or another way of saying it, b is, so 7 is 3 plus 1 times 4. Or another way of saying it, what is this saying? This is saying that 3 is 0 times 4 plus 3, and 7 is 1 times 4 plus 3. So they have a different Q, but they have the same R, and this means that they're congruent. Let's have another example. So 15 is congruent to 37 mod 11. And let's just check this in a few different ways. Their difference is 22, which divides 11. So 15 plus 2 times 11 is 37. And here, how can we write these? So 15 is 1 times 11 plus 4. And 37 is 3 times 11 plus 4. So they have the same remainder. And from these equations, you can also see that these are, again, congruent to 4 modulo 11. So that's actually an important example that I want to point out. In the division theorem, which of course is very much coming from this third way of saying the definition, we have this equation like this. So we get A is congruent to R mod D. And in fact, this is very important because if we think about what the division theorem is telling us, it's telling us that this R is unique as long as we impose the condition that it's between 0 and D. So this tells us every integer is congruent mod D to exactly one of the following things: 0, 1, 2, up to D minus 1. So these are the different classes or the different representatives of what things can be congruent to modulo D. And I hope I'm not being too confusing by switching between D and M. They're different letters, but of course, we'll treat them exactly the same way. So let's have an example of this. Basically, the importance of this is that it's convenient to use this finite list because it makes things much easier to work with. So let me not write mod 5 at the end of everything, but we're going to be working mod 5 in this example. So 17. So mod 5, we have this list 0, 1, 2, 3, 4. So everything is congruent to one of these things. Which one is 17? So 17 is 15 plus 2. So it's congruent to 2. And then 18 is congruent to 3. And 19 is congruent to 4. And 20 is a multiple of 5, so it's congruent to 0. And then 21 is congruent to 1. 22 is congruent to 2, and so on, in both directions. You just cycle through this list of 5 elements. So this is what it means to work modulo some integer, mod m. So what is modular arithmetic? It amounts to basically the following theorem, which I will say a sort of slogan first, and then I'll say the precise statement. So the idea is that arithmetic works correctly mod m. So essentially all the rules of arithmetic you're used to, everything still works right. And what do we actually mean by this? So let me write the statement. If A is congruent to B mod m, and C is congruent to D mod m, then A plus C is congruent to B plus D, and A times C is congruent to B times D. So let's take a second to unpack this. I'm going to say two more slogans about this, and then we will talk about it some more. So what is this saying? I want to say it two different ways. So first, if you're trying to add two numbers, mod m, you'll get the same answer, you'll get the right answer, not depending on which congruent thing you took to start with. So that's maybe a bad way of saying it. Let me try and make that more clear. Get the same sum or product, regardless of A versus C or B versus D. So let me give an example of this. Let's say what is 20 plus 45 mod 3? Well, let's do an example in the style of the theorem. So let's say A equals 25, and let's take B to be something that is different from 25, but congruent mod 3. So let's say B is 10. These are congruent mod 3 because their difference is 15, right? And then let's say C is 45 in our example, and D, what is something that's congruent to 45? Maybe let's just take 30, because again, the difference is 15, so these things are congruent mod 3. And then when we add them, so 25 plus 45 is, uh-oh, gonna have to do arithmetic. This is bad. 60 plus 10, 70. And then what's C plus D? Or sorry, this is A plus C. And then B plus D is 10 plus 30. It's 40. So the upshot is that these are different numbers, but they are congruent mod 3. So arithmetic still works in this sense, that you get the same sum as long as you consider the sum mod 3. So that's the first upshot of the theorem, that the sum you get doesn't depend on where you started from, as long as they were in the same, as long as they were congruent to start. The second thing I want to say is that this means we can reduce mod m at any time. So I might use this, what does it mean to reduce mod m? Means choose the corresponding thing in this range like we talked about before. And this is making it really, really easy to do modular arithmetic because you don't have to do any more complicated arithmetic than you get from just these numbers. So for example, what is, let me write down this example just so that I don't have to redo it. This thing times so here are two big numbers. What is their product? Mod 3. So the point of this slogan is that we don't have to multiply them and then reduce mod 3. We can reduce mod 3 first and then multiply them, and we'll still get the right answer. Or either we'll get the same answer, either way we do it. So 2137. Oh, let me change this so it matches all of my notes. I want to say mod 5. Doesn't change too much. But let's remember, what is our rule for divisibility by 5? A number is divisible by 5 if it ends in a 0 or a 5, right? So we can find the remainder by looking at what's the next smaller thing that ends in a 0 or a 5. So it's this thing, in this case, which tells us that this is congruent to 2, because the difference here is 2. Mod 5. And this thing, again, the smallest multiple of 5 less than it is this. So this is congruent to 3. Mod 5. So this big product that we don't want to have to evaluate is going to be congruent to 2 times 3, because we can just replace both of these things. And this is congruent, this is equal to 6, which is congruent to 1 mod 5. So this makes it much easier to do modular arithmetic than to do usual arithmetic. And let's get another sort of example of this. Or, let me just say, I did do the product on the calculator. And just as a check, what is the product? It is 10,563,191. And by the same test, we can just look at this last part. The last digit is 1. So that tells us that it is congruent to 1 mod 5. So we got the same answer, just as we expected. Get a new page with us. We're running out of space. So now that we have done a little bit of discussion, let's see a proof of the theorem. So I'll prove the addition part. The multiplication part is very much the same. So I'll leave that as an exercise. So let me rewrite it, just in case we've forgotten what it is. If A is congruent to B, and C is congruent to D, then A plus C is congruent to B plus D. So I'm just replacing each guy with something that's congruent to it. So what is the proof? It should follow essentially from the basic divisibility rules that we talked about at the start. But here is one way we can write it down. So A congruent to B mod M. As usual, let's start from the definitions. In this case, we have a few definitions to choose from. So starting from the definitions can get a little bit trickier when you have more than one definition to choose from. But again, let me encourage you to try things and see what works and learn from there. So I'll skip that part for now and just tell you which one is going to be convenient. So we're going to use the definition that B equals A plus a multiple of M. And similarly, C congruent to D means D, could write either one, but D is equal to C plus a multiple of M. And then we simply add them. And then do these substitutions, see what we get. So we get A plus S times M plus C plus T times M. And of course, we can rearrange this as A plus C plus this thing. Let me just factor out the M immediately. We get M times S plus T. And now if we look at the two sides of this equation, this is telling us that this thing is equal to this thing plus a multiple of M. And you'll remember that that is the definition of congruence. So A plus C congruent to B plus D mod M.